being advanced to meet their national needs. Thank you, Dr. Gong, for your time.
Yeah. Thank you for Vijay and welcome everyone to join this meeting. I'm Jiandong Gong. Just Vijay have an introduction for me. I will take this chance to take some introduction about the GRIPS global forecast systems. The first I will give a quick review about NWP Center of CMA. NWP Center is very like the EMC here. It's a national level for the numerical weather model development. In China, the weather model and climate model, they are developed separate. We have a infrastructure very like the ECMWF. That means we have a research division majorly for the global and the regional model development and also for the data collection and pre-quality control. We have six sections for the dynamics, for the physics, for the data simulation, majorly for the global and the regional systems, parallel computing, and data pre-processing. We also have an operational division. It's focusing on other systems such like ensemble prediction systems, technical forecasting, environmental application, and all others connect with the model operational part such like product verification and the system maintain. We have 5 of section over there. We have very small manager group, majorly for the multi-duty for the NWP Center. So today I have 4 talk about the global model for the GRIPS. The first is the development of about what's the GRIPS systems and how the standards of these systems. The GRIPS The GRIPS is short for Global Regional Assimilation and Prediction Systems. It's a grid model systems. It's a unified systems. That means we have a common dynamic code for the global, regional, and different applications, and with a different configuration of the physics for the global and the regional. They have 4 basic components. That means for the variational data simulation part, unified dynamic code, physical parameterization scheme, and parallel computing. So the first of these model systems is initialized in the year of 1999, in the year of 2001. This system is sponsored by the Minister of Science and Technology of China and also from CMA. So in the year of 2003, the first unified dynamic frame was set down there. And because our model system, the global data simulation and the model developer separate. So at the very beginning, we developed the pressure level 3D VAR. So in the year of 2006, the first version for the GRIPS method is put out in the operational running, and in about 2 years later, it's used model level 3D VAR. So in the year of 2012, the operational GRIPS rapid analysis and forecast system put in the operational running, and then in the year of 2013, it's used GRIPS Typhoon forecast for the version 1. And in the 2006, for the GRIPS GF Global Forecast Systems is put operational running. This is the first time we use operational running the global forecast systems. At the same time, for the regional prediction systems, in the last 2 years, there are at least 6 of model upgrade in the operational. That means the first in the year of 2018, we put operational running for the GRIPS 40 VAR, and also for the GRIPS global ensemble prediction systems and other metal scale systems. We also have a 3 kilometers model. For others, for the GRIPS TYM and the regional ensemble prediction system, also upgrade to version 3. So here is all our systems. Listed here. The first is for the data simulation. We both for the global regional data simulation, we have one system. In fact, it uses option to control its running for the 4D VAR, 3D VAR for the global, or for the regional for the 3D VAR. For the model part, the dynamic core similar. Especially for the regional model, we have a unified model systems for the deterministic forecaster, for the regional ensemble, and for the typhoon forecasting, and for the high resolution. Here I list the model for the different applications, such like for the 20 forecast, for the global. Currently, we have a 25 kilometers resolution. Also, we have a global ensemble prediction systems. Because we develop a 4D VAR, so at the same time, so we use the singular vector and linear physics for the global ensemble prediction. And for the regional systems, we have two of them. The first is 10 kilometers for the 3-hour rapid analysis, and also we have 3 kilometers mesoscale model for all over China, such like this big domain. For the typhoon forecasting, we have very large domain over here. It covers the Indian Ocean and the Western Pacific. The resolution about 9 kilometers. So this the second part, I will introduce about the development of the global model. Here is the main feature of the grips dynamics. Just as I said, the grips dynamic, it uses low hydrostatic compressible shadow equations. It uses Arakawa C grid, but we put a V point as a polar. And in the vertical is Charlie fitting piece vertical staggering. For the horizontal is longitude, latitude, and height based carry following coordinate, such like this. For the reference is isothermal atmosphere. And for the time integration, we use off-centered two-time level semi-immunity, semi-Lagrange time stepping. We also use a three-dimensional vector for momentum equations and use the surface sphere and polar effect of trajectory calculation. We use a preconditioned GCR solver for the Helmholtz equation, and for the scalar variable advection, we use the piecewise rational method, or we call the PRM. For the other techniques, such like low vertical interpolation for potential temperature for the depart point, and we also use doubling damping to control noise for model. In the last 2 years, there are several of the major improvements for our model dynamics. The first is we use a three-dimensional reference. And the history, we use only one-dimensional reference. That means we use isothermal atmosphere like this. So the problem for this is the perturbation is quite large. This for the potential temperature perturbation over here. We can see for some areas, such like high levels and other levels, they are very large perturbation value, even have almost the same order as a reference value itself. So when we introduce 3D reference, yeah, if we use a 3D reference, this 3D reference is a hydrostatic balanced value. It uses the month averaged field, and it not change during the iteration. So we can see that the potential temperature perturbation is very smaller compared to the original one. So we also do some testing for this 3D reference. Here we'll compare others with dynamic curve from UK Met Office, and also from dynamic curve from here. We can see these are our two systems, one from 1D reference and another from a 3D reference. you can see for the GRIPS 1D reference, the sum wave description for the north hemisphere is not, in fact, is too smooth, and it also in the north hemisphere you can also see some change over here. But for the 3D reference, we can compare these two. They are quite, it's good enough than the 1D reference. So we also compare the kinetic energy spectrum for the different wave. The red lines for the 3D reference and the one red lines for the green lines for the 1D reference. We can see that these blank lines for the best result. We can see that with 3D reference is good. Compared to the end game, they also not as similar, but it's quite similar as the FV3 for the old version. So the second improvement is for the dynamic change is we use predictor, corrector, semi-immunity, and semi-Lagrange scheme. That means for the traditional semi-immunity and semi-Lagrange scheme, we use only one times to solve the Helmholtz equations. That means when we calculate the middle point velocity, we use the wind from last time level and time level from t, and use extra interpolation to calculate the middle point solver. And then we calculate the depart point position, and we calculate the nonlinear term on the n+1 time levels, also use extrapolation calculation. And then we solve the Helmholtz equation and other variables. This is the traditional one. For us, we do this for twice. The first is use the traditional way to do the prediction and then do correction. For the second time, the middle point velocity, because we already have a value for the t plus delta t, so it's just interpolation. For the nonlinear term, because we already have a value for the t plus delta t time, so we can calculate directly. So so with this modification, the first is reduce the noise. The second for the off-center coefficient. In the history, we only have a very large value for this from 0.72, but now we can reduce this to the 0.55. And also increase the time steps. The third change for the dynamics is we use new spectral filter terrain. These are the old ones, the new ones we use a spectral filter. There you can see much more structures for this. One of the benefits from this, we can see for the different real potential height, such like 12 kilometers, the vertical velocity, the color show here. This is because forcing by the topography, you can see the vertical velocity is increased. So we can see from here, for the old systems, because it's smooth too much, so for the 8 delta x, after 8 delta x, for the short waves, it's damping too much. But for the new topography, show as this lines for the 4 delta x, the after 4 delta x is the energy is damping. So it seems that we use a high resolution model topographies. The model performance is also increased. So I summarize what we have done for the model dynamics change as this graphic, this table shows. The first is the reference from 1D to the 3-dimensional, the first one. The second is how the time integration scheme from traditional to the predictor corrector schemes. And for the terrain, we use a Raymond filter to the spectral filter. Another most big modification is a filter. In the history, we have many filters for the model, such like horizontal filter, QV filter, red diffraction, like this. But now we remove most of them. We keep the W damping and really fraction for the model top. So one of the benefit is the just as I said, for the semi implicit coefficient, it's changed from 0.72 to 0.55. This is the first. And another is we can take a much larger time step. That means we have 20% faster than original one. So what's the result? This is our 40-watt cycling systems for this modification for the model dynamics. If we see the ACC of the North Hemisphere and the South Hemisphere, they are slightly benefit. But if we see the mass conservation, we calculate by this from surface pressure. We can see in the history, the old version for the 8 days forecast, for on average, it will have a mass loss about 0.7 millibar. But after modification for the new systems, for the 8 days forecast, we only have 0.2 millibar forecast. For the forecast score, for red lines, it means better. For the green lines, it means worse. The color is fully different here. so you can see that with the new dynamics for the Eastern Asia, that means the domain for the China and the North Hemisphere, South Hemisphere, and the tropic. You see for the most of variables, the performance, the modification or upgrade of the grip systems dynamics in fact have a benefit. This is the first job we have done. The second job is for the grips physics. The first we should understand that for the grips in the vertical grid, we use a Charlie Phillips grid, like here. In this grid, for the potential temperature and humidity, we defined in the full level. But for the physics, several of the physics, it in fact defined in the half level over here. So when we use physics, that means we have to do 2 times interpolation. The first, we should interpolate potential temperature and humidity from full level to the half level. And then after we got the tendency of the potential temperature and Q, we will interpolate again to the full level. This should be full levels. So what happened? Just as we see from for the boundary schemes, we can see it will have some confusion mode like this, both for the temperature and for the humidity. So the first thing for us to do is we rewrite the PBL scheme and make it on the Charlie Phillips CP grid. After modification, the blue lines just shows after the modification for the distribution of the temperature and humidity in the vertical. It seems much better. This is the first modification. The second modification is for China self-development double momentum macrophysics schemes. We also rewrite this macrophysics in the Charlie Phillips grid. In the history, we always find some problem for these macrophysics schemes. We find a very large, unreal for the humidity in the vertical over here. So in history, we use a QV fixer. That means we just remove the moisture above the tops of the troposphere. After we rewrite the macrophysics in the CP grid, like these red lines show here, we can see that in fact this QV fixer is not needed. The performance of the QV is much good, if we show some figures over here, like these red lines, the orange should be here. This is uh, not real distribution of the moisture. After the modification, you can see it's much better. And another modification for the physics is for the surface line. We also improvement to match Chinese Phillips grid over here. There are lots of calculations such like use new gradient extrapolation for reasonable surface T and Q, and we can see the modification result. Before the modification, for the surface have a large area over here, but after the modification, the area in this area generally decreased a lot. So we can see the performance for compared to the ERA 5. This for the 925 millibar over here. This can be as a reference. For our old systems, for the stratocumulus, for the cloud water value, you can see they are almost they are very smaller cloud water over here. But after the modification, you can see clearly that the forecast result is an improvement. This is also true for the 850 millibar. We can see from ERA analysis, it looks like this one, but for our original version, it's not good enough. For the modified system, it's much better compared to the original version. But it seems still some more cloud water over here. So we do the 40-watt cycling experiment for this physics modification, also for the summertime from January, June to the August, and also for the winter time for the December to the February. The rate similar, the rate for the best. So you can see after physics modification and upgrade, we have got the good result. This graphic shows the moisture belts. We can see for the original systems, it have large belts, especially in the tropical region. After the modification, the belts is increased about 40% for the 5 days forecast. In fact, for in the tropical region, for the root mean square area of the temperature, wind, for the winter time and summertime, it also increased dramatically. This is the development of a global model. The second is upgrade of the global data simulation systems. In the last year, we have the very major progress for our GRIPS global systems is data simulation improved from 3D watt to the 40 watt. We have done lots of work for the 40 watt systems. The first is improve the 40 watt computation efficient. There are lots of work to done, such like larger scale parallel computing and improve agent code computation efficient. Parallel I/O optimize the memory space usage. Because our system only use one executable code to run in the out loop, for the in loop, for the trajectory calculation, and also for the iteration calculation. That means lots of variables in fact stored in the memory. So we not use a disk to writing and reading the trajectory state variables. And also we use more efficient minimization algorithm. At the same time, the time slot is increased to the 30 minutes, more data used, and we use linear physics. In the year of 2018, we only use dry physics, but from this year, we also use moisture physics. We also use a digital filter as we constraint for the noise control For the satellite data BIOS correction, we use auto-update BIOS correction for satellite data, especially for the AMS UA. So what's the result from 3D VAR to 4D VAR? Here is a 1 year result. The black lines for the 3D VAR and the red lines for the 4D VAR, the dashed lines for the background. So we can see for the North Hemisphere, for the geopotential high, the 4D VAR can almost get 6 hours benefit to the 3D VAR. That means even the background of the 4D VAR is even better than the 3D VAR analysis over here. So if we see some levels such like 500 millibar, we can see for the 3D VAR analysis, it always have a larger error, root mean square error than 4D VAR systems. But we also find some benefits that when we use 3D VAR for some season, such like from September to November season change, and it will have a very large areas for the 3D VAR. But with 4D VAR, with very strong mode constraint, the root mean square error is much smooth. So this is a scorecard for the 4D VAR compared to 3D VAR for the 1 year forecast. You can see clearly for the Eastern Asia, we can get benefit for about 4 days. For the North Hemisphere, for about 6 days. For the 6 days. For the South Hemisphere, almost for the 10 days benefit. For the troposphere, it also have a very good performance. This, I think, is a very big step for our GRIPS global system upgrade in history. If we see the typhoon check forecast, we can also compare 3D VAR like this blue lines and the GRIPS 4D VAR. We can see from here that the performance of the GRIPS 4D VAR is better than 3D VAR. Generally, for the short-term forecasting, such like 24 hours forecasting, we can get about 12 to 15% of the improvement. For the long-term forecasting, we can also get about 5 to 8% improvement for the typhoon check forecasting. This is a sample from 2016 from for the typhoon for the number 1 to number 25. So after the GRIPS 4D VAR systems upgrade put in operational in this summer, just several months ago, we take the 4D VAR systems upgrade again. The upgrade include several of them. The first is for the linear physics. We put the new SAS convection linearized physics in our 4D VAR systems, because nonlinear systems is new SAS. We use simplified new SAS. Another is larger scale condensation. We use a Tompkins scheme. That means we calculate the evaporation and condensate of the larger scale condensation. We consider the cloud as one of the condition, and this is significantly improve the analysis and forecast. And the second is we use hyperspectral infrared for the metal A, B, and Z data. We also improve the satellite readings BIOS correction scheme. Another improvement is for the decorrelation scale I will introduce later, and also include other improvement for our 4D VAR systems. So the first is linearized moisture physics. Even it's a little bit hard to maintain, but the benefit is clearly. This shows two linear physics. The first is deep cumulus convection schemes, and the other is macro larger scale condensation schemes. We can compare if we use moisture physics or only dry physics, and it impact on the area reduce on the area reduce. In the summertime, we can that the area can be reduced about 7% for the summer, and in the winter time it can be reduced almost 8% in the winter. So these negative values means when we use the moisture physics, the performance is improvement, but for several, but we think is performer is okay. So we can see the performance on the forecast. So for the 500 millibar drill potential high for the north hemisphere, the red is for the with moisture physics, the blank for the dry physics. We can see clearly the benefit almost for 10 days. And for the tropical region, with moisture physics, it have a good impact for the temperature forecasting and wind forecasting. Here shows the graphic we see in the north hemisphere, south hemisphere, and the tropic for the wind. It have a good impact, but for the temperature, especially for the root mean square area, they still have room to improvement. Another is we use ensemble information in our 4D systems. That means you know that when you use 4D data simulation, that the analysis increment in the 4D at the beginning of the 4D window or at the end of 4D window, they should be consistent. But for our old systems, just as this graphic shows, this is the variance, this is the spectral, and the green lines for at the beginning of 4D window, and this purple blue lines for at the end of 4D window. So at the very beginning, our analysis at the beginning of 4D window show as these yellow lines. But after we use some new techniques, such like we merge the second order auto-regression schemes and filter the EDA members, we use merge the background. It looks the shape like these ones. So the performance analysis increment at the beginning of the 4D window and at the end of 4D window, they are very consistent. So after modification, we can see the performance, especially for the north hemisphere. We can also get the benefit almost for 8 to 9 days. This is the final. We get the result from last year modification. We can see we do test for the January, August, September. In fact, we do more than half-year test. The performance better. This is the second time, so we also have a very big step improvement for our 4D systems. So the third of my talk is talking about the global ensemble prediction systems. Just as we know that because we develop a 4D system, we have a tiny linear model, agent model. We also have a linear physics, and this technique can also be used for the singular vector ensemble prediction systems. In history, we use a global spectrum model from ECMWF. It uses the breeding vector for the initial perturbation. The forecast about 15 days. For the GRIPS global ensemble prediction systems, we use a singular vector or SV method. We use SV both for north hemisphere, south hemisphere, and a single vector for target over tropical cyclones. That means if for every tropical cyclone, we can do a singular vector target for these tropical cyclones. And currently, we use a linearized, simplified PBL scheme and mountain blocking schemes. And the optimization scheme for the single vector is 48 hours. The Landos iteration for resolve this single vector for 50 times. And the horizontal for the single vector calculation about 25 degree. and vertical level is 60, and we rescaling single vector based on standard deviation of the analysis error, and we also linear combine the single vector to get sample the initial perturbation. So finally, in operational configuration, we have 31 members with 0.1 degree resolution. The control run is from Grace Gibbs 0.25 degree resolution. We also consider some model uncertainty in the global forecasting, such like we use stochastically perturbed parameterization tendency or SPPT schemes and skip schemes. The forecast length also 15 days. I give several structure about our GRIPS singular vector systems. The first is for the first single vector. This at the initial time we can see the the distribution of the first single vector like here. If we see the line along this, we can see in fact for the singular vector is the structure of the perturbation is west tilt. That means it's in fact is baroclinic structure. This kind of mode can be the error can be increased very quickly. So after 48 hours forecasting over here, you can see most of structure almost be a barotropic structures. So in our systems, we combine these two from this. We combine these two to have a finally perturbation. The result from our systems compared to the ECMWF, they are very similar. At the same time, we will also test the energy normal of this structure. The blank lines for the initial times and the red lines for the 48 hours forecasting. We can see that the energy, both for the total energy and kinetic energy involved during the time, you can see that clearly at the beginning the energy distribution like this, they have two directions. The first is to the middle and high troposphere, and another is in the lower of the troposphere. We can compare this structure with ECMWFs. We can see it's quite similar. Even for the involved single vector, when we in the spectral space from initial single vector and involved single vector, we can compare these two. They are quite similar. So we compare our singular vector system with the GRIPS ensemble prediction systems. Also the red for the good, we can see for the eastern edge region, for the north hemisphere, south hemisphere, and the tropical region. This for the 10 days forecasting, we can see for most variables, such like parameters, such like this only for the CRPS score and ensemble mean root mean square error. You can see for the wind, temperature, gel potential high, almost all variables have have better than the old spectral global ensemble prediction systems. Much better for the CRPS score. For the accumulated precipitation forecasting, we use the Brea scale score and the reliability to compare. The red lines from GRIPS global EPS and the blue lines for the spectral EPS. We can see that for the 0.1 millimeters precipitation, the GRIPS global ensemble prediction system perform better. But for the 10 millimeters, it's also good. For the 25 millimeters, it's almost it's good for the beginning, but it's neutral after 2 to 3 days forecast. This for the reliability diagram for the global EPS and the T639 EPS. For the 0.1 millimeter, 5 millimeter, 10 millimeter, and 20 millimeter. For the lower precipitation, the Grips GPS is better than T639 EPS. For the larger precipitation, it's almost equal. So, final talk, I will give a review about the future plan of our systems. The first we have done is we use new Grips dynamic code with the model top rise from currently about 36 kilometers, 400 millibar to 87 levels, 3 kilometers to reach 0.1 millibar. This is work we do in this year. There are lots of tasks needed to do for this. The first, we use a new dynamic code, just I report in the very beginning of my presentation, such like a 3D reference profiler, predict correct semi-city and semi-lockdown schemes, and new spectral field terrain. For the physics, we have several of them to be done. The first is consider upper stratospheric moisture source due to oxidation. And also we consider the non-orographic gravity waves. And another is the mitigation model error related to the moisture physics. For the data simulation, we also have lots of work to do because model top is increased with some work such like new background error covariance, especially for the middle troposphere. And we also do the modified and upgrade global timing linear and adjoint method because the model dynamic have a big change. Others is update linear physics, such like new source convection and Tompkins larger scale condensation to match these model levels increase, especially in the troposphere. And the digital field constraint, in history we use weighting from background error, but now we will change to use the total energy norm. And also for the RT-top, we will increase, we will update to 12.2. Others include use high-peak satellite channels in this system. Another change of our systems is to increase the Grips global forecast model horizontal resolution. We have tested the global forecast resolution from 25 kilometers to 12.5 kilometers. This is a test majorly for the computation efficient. If we add more nodes to calculate, such like we use a 512 node to calculate the global model, we can use about 78 minutes to perform the 10-day forecasting. This is the first. Another is ED ensemble-based Grips in 40-watt systems. When the 40-watt is developing, at similar time, the hybrid system for the 40-watt is also developing at similar time. Here is some major improvement for the ensemble 40-watt system. The first is alpha quantum variables is introduced in the 40-watt systems. It can be done for the 2D or 3D localization, and it uses balance preserving localization. That means localize only use analysis variable, not on the state variable. And the ED ensemble members is not from ENKF, but from a group of 40-watt analysis with perturbed observation and perturbed SST. The mode uncertainty will majorly we use from ensemble groups such like STPP and SCAPE. One of the most big improvement for our systems is we use preconditioned lenses conjugate gradient method. That means if we calculate the engine vector for the first time, we can repeat to use again with less than only use half iteration. That means for the original one we may use 50 times iteration, but for the new one we can only use 20 of them. So this will accelerate the ensemble for very efficient. We also use other techniques such like valid time shifting perturbation method. That means we use the ensemble with a small EDA ensemble, but we use the perturbation 3 hours early and 3 hours later. So with the EDA 40-watt systems, we have we have carefully calculated the waiting for the climate and the ensemble part. This scale for the sometimes 52 days scale and winter times 52 days scale. Even 40 watt compared to the 40 watt. You can see with the even 40 watt, for the first 2 days, for the north hemisphere and the south hemisphere, and for almost 4 days for the anomaly correlation and for the root mean square error for the 8 days, we can find the benefit from even 40 watt systems compared to the 40 watt system. For the winter time, the performance is similar to the sometimes, but a little bit better. So in future, we will combine these two of the perturbation method. The first is from EDA and another from single vector, and we use these two in our global ensemble prediction systems. Because EDA have a much better in the tropical region, and single vector have a much better for the extratropical region. So we will combine these two. So how about the systems in the 2020 to 2021? The first, just as I said, the global system resolution will increase to 12.5 kilometers for horizontal and 0.1 millibar in the vertical. The GRIPS global ensemble prediction system, currently we have 50 kilometers, but in the year 2021, we will have a new computer system, so the resolution will increase to about 25 kilometers. For the GRIPS mesoscale systems, currently they only use a global downscaling plus cloud analysis. But now, in the year 2020, we will use a 3-hour rapid analysis forecast of the systems. For the regional systems, we will have a small modification from 10 kilometers to the 9 kilometers. And for the Indian Ocean, Western Pacific is similar. We are very likely that in the year 2020, for the global data simulation, we can use 40 watt or even 40 watt as an option for here to use of this. So how about the future? Here I gave a roadmap for operational NWP development. This some of them based on the National Meteorological Center 2019 to 2025 implementation plan. The first we show here. Currently we are here. Global GFS 25 kilometers level 60 and global ensemble 50 kilometers level 60. And we have lots of work to do. I have introduced such like a 3D propeller, predict the correct semi-immunity seminar ground scheme, 0.1 millibar model top, high resolution, GRIPS global satellite data simulation, physics bells mitigation, ensemble of the 40 watt, single vector plus EDA for the global ensemble prediction initial perturbation, linearized molecular physics for the single vector calculation for the 48 hours. This all will be done for the year of 2020 to 21. Another is a new system based on EM40 watt in future. And similar time for NWP Center of CMA, we have a research on next generation model. It's a multi-momentum finite volume dynamic core, or we call the MMFB3. It's similar to the FB3. Currently, the dynamic core structure is set up. We do dynamic plus Kessler microphysics to do more tests. At the same time, we develop the coupler, and in future, we are very likely to continue use the 40-watt technique. Some work will be done for the linear dynamic core for the 40-watt, and we continue develop this for the next generation models, such like more sentinel data operator in the 40-watt systems and other tests. So we wish that in the year of 2025 or a little bit earlier, new model systems based on multi-momentum finite volume and 40-watt or even 40-watt can be used for the operational running. This is our future choice. Just as I showed here, currently we are grip systems. We also know that the other research institute in CMA, they develop some new model dynamic core, but we develop a multi-momentum constrained finite volume method. So we wish that the 2025 will be the timeline for our two application of the new model system. I guess this is all my presentation, and because the time is limited, I'm sorry I speak faster and maybe lost lots of detailed information for our RIX global focus model. So, thank you.
Time for questions.
Do you have any plans to use in the future a polyhedral-based grid for global modeling, like the cube or icosahedron?
Yeah, Xinliang, could you take feedback? Could you repeat the question about heat to the dynamic?
Do you have any future plans to use a grid based on a polyhedra, like a cube or an icosahedron, instead of using an
grid. Change different grade. Yeah. Actually, yeah. We have tested shallow water models on the different grids, like the Jiandong grid, and the Cape grid, and the icosahedral grid. But in currently, we developed a three-dimensional model based on cube sphere. But in near future, I think we have planned to implement it on icosahedral, it's very uniform, something like that. We have a plan.
Thanks.
Yeah, please.
Yeah, go ahead.
I saw your single vector target typhoon, right?
Yeah.
It's a global-wide target or only West Pacific?
For the target, only for the typhoon region. If we have one typhoon, we have 10 to 10 degree target over this region. We do a single vector for this tropical cyclone, and for another tropical cyclone, we repeat again 10 to 10 degree.
Yeah, my question is, okay, like today, global, we have 10 hurricanes. Or tropical, we target 10.
Yeah.
Right?
Yeah,
It's
because the
global-wide.
because single vector calculate very fast, but it's a global one because you use global tangent linear and agent mode.
Right.
Yeah.
So, and any like much improvement for hurricane forecast?
Yes.
After
Yeah.
With or without?
Yeah. It's have much improvement because there are several parameters can be tuning for this parameter. We have test for the best parameters to do this, and it's I think it's much better. Could you give some more feedback?
For hurricane forecast.
the track spread is increased significantly because the TC targeted singular vectors could describe the initial uncertainty around the TC.
It's a nice introduction for the forecast system. I believe the surface boundary is an important part of the forecast system. Give a brief description for the surface like ocean SST, CRS, and land surface. It's treated in the BA initialization part and during the forecast.
Yeah. Currently, we in fact we not do the surface analysis. We majorly for the atmosphere analysis. We began to for the regional model for the land surface data simulation, but for the global is only use the climate, initial condition. We have planned to do this in the next few years. Even for the sea ice or snow analysis. It's we're not done currently.
Thank you.
They do use the OIS as their model in the species, but not change.
What's the surface scheme you use?
For what?
Surface scheme and the surface and the surface on the global. How about the forecast of the surface field?
Yeah. Here.
No surface layer scheme.
Surface layer schemes. Who can ask this question? I'm a data simulation group. I know.
It's physics.
Yeah, but I know, but it's 那个莫尼诺波夫那个。Yeah. This.
Just a theory.
Yeah.
I mean, how about the results about the surface fields forecast, like temperature?
To limit the temperature forecasting for our global forecast system, it have they have a diurnal cycle error. You can see from daytime, nighttime. It's have a bells different, especially at winter time. At night time, we can see the bells. For the over China region, we also find there are a little bit larger areas for the 2 meter temperature, such like 3 to 5 degrees. It's We
How is your current grip system compare with other group systems like EC?
We are as a WMO leading center. We have we send the forecast skill to the WMO leading center. I guess you can find the verification score from the web page. They can download for every center. You can just find them.
I saw one result from the GRAPES regional EPS. And the precipitation forecast is better than the
Depend on case.
I think over 25 millimeters.
Yes. But for the ECMWF, for the moderate precipitation, it's the best of all. I mean, for the it's a very strong precipitation for regional ensemble prediction perform better, and for the it's also better.
Only 10 millimeters.
5, 10, 20 like this range. ECMWF always best. Depend on case.
Yeah, very impressive talk. So for the great typhoon models, do you have any plan in the future to add the nested domain, moving nested domain?
Yeah, we already done this. We have testing some.
But this one you are talking about, there's just one domain, right?
Yeah, just yeah.
9 kilometer.
9 kilometer domain. We have cooperated with other institutes. They use moving testing more than. I guess this work already have done more than 3 or 5 or longer time. It's I mean, it's in the semi-city and semi-Lagrange framework is sometimes it's a little bit difficult to do this. They have to do some cases study. You can see the moving of the nest, following the typhoon moving, and you can use different resolution for the center. Yeah, we do this. If the technique is mature, we will put in the operational, especially for typhoon before the landing, like this. Yeah. Yeah. So Homa, I guess we'll give more detail. Yes.
The improvements of the ACE score by the microphysics is really important. My question is, how many more forecast variables do you have? Microphysics.
Uh-huh.
How many forecast variables? Snow, ripple.
How many forecast variables from the microphysics?
5. I guess 6 of them, or 5. 6 of them, I guess, because it's because this microphysics for us from China development. The first they use for the weather modification, so it's a very complex one. It's I mean, it's, yeah, I guess it's a 6 or 5 of 5 hydrometers, I guess.
Including the lumber concentration, right?
Uh-huh.
Mixing ratio and lumber concentration. The total shall be 10 more.
He said double more.
Double moment.
Yeah,
It's a double moment for the global. Yeah.
How much is the computer cost? Overhead?
Yeah, it's need a longer time, but yeah, it's need a longer time, especially for the global forecasting. But the person developed this, he think is we can affordable for this. But Xian, could you repeat?
I have no idea, but I'm not tested what's the momentum to momentum physics cost at that time. I cannot understand.
Yeah.
From your plan, it looks like from this year to next year, your global model resolution will double.
Yes.
From 25 to 12.5.
Yes.
That means you have a big computers.
Yes.
Right?
Yeah. 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 CMA.
We show the timing. Yes. Yes.
Yeah.
Yes. This one. Timing.
Yes.
Okay.
Yeah.
For next year.
Yeah. So yeah, in fact, the CMA have a plan for next supercomputer. Currently, we have 8 to 9 pflops. They want to triple the computer resource. Yeah. In the year 2021, they already have plan because the space for the computer is ready. I mean, so they have 2 locations. One in the headquarters of CMA, another is just in the Xi'an province. They are far away from CMA headquarters. So the only one thing they need to do is just buy the supercomputer because the infrastructure for the environment is okay. Yeah.
All right. So once again, thank you for giving a wonderful seminar and impressive progress. We should be celebrating on that. Thank you.
Yeah. Thank you. Thank you for your.